Alright, hi everyone. Hi Dr. Dimitri. This is Luciano Vilas Boas here, and I'm here today to present my research, my study on obesity levels using data science. So my mindset for this project was following some of these approaches here, looking for missing data, not avoiding this type of illusion of perfection here, and working with the 80-20 rule, which you guys can read here. I think it will make sense. Don't reinventing the wheel. Sometimes, most of the solutions we can find out there and just customize that to our need. Remember, data sets are unique, so there's no such a thing like one size fits all. So you're gonna have to do your job anyways, but it's good to kind of have some sort of a benchmarking to start from. And I have this in mind, fast and dirty. So I want to, come up with some sort of a pipeline or some sort of thing that will give me some, overall information about the data set. And that's what I did here. So the idea is to get some intuition about the data and see what the data is telling me, and fail fast. If I'm messing up with my codes or with the results that I'm getting are not, good enough, so then I want to figure that out as soon as possible, not waste, months working on that to figure it out. 6 months later, that's all garbage, right? We don't want that. And finally here, attention to imbalance and classify. Every time you're working with some sort of a classification problem, you should look for that. So those are my mindset, and this is my project proposed just for the sake of documentation here. Data set I got from UCI Machine Learning Repository, and this is the paper that actually comes with that data. So some of the definitions, they had 16 variables, and you can see how they classify here. This was an online research survey, and out of these they came up with the 7 levels classifier here, which goes from underweight to obesity level 3 here. So those are some of my initial questions. I was just intrigued, just trying to figure out which of these variables will be good to to predict obesity or those type of issues. So this is the classification, the balancing that they actually did, not classification. So they start with this data, that's the original data, and then after the classification, that's what they came up with. One thing that I was intrigued was why the normal weight here was so high here, and then when they balanced it, the obesity one got actually even bigger than what they had before. I'm not very familiar with this mode technique to balancing data. I don't actually use it. I use rows, and you're gonna see that example of that, and that's kind of the original records, and then after the balancing. Exploratory analysis here, I was looking for missing data. We didn't have any missing data, and I created a new feature here with 2 variables, which 0 will be not obese and 1 obese, and I also created another variable with 3 variables, not obese, overweight, and obese. Why I did that because I wanted to trying to simplify things and not having 7 different levels of things. I think sometimes simple is the best thing to do when try to talk what's going on and convey the information. So the question that I had was, okay, I create this new variable here. Should I balance in this new variable? Because it would be something that from what I could notice, something like taking an average out of an average. So you usually don't do that. So I'm not 100% sure if I should have done this here or not. So exploratory analysis here, we have a histogram. Funny enough, you have here the height, almost like a normal distribution. And then we have the skewness here and the kurtosis. I'm not gonna have time to explain that, I'm sorry, but you're gonna have to search for yourself. I'm so sorry, the time is very short. And then the exploratory analysis here, this is kind of a scatter plot, but because the data it's actually binary here, that's kind of the way it looks like. So you can see here the female, which is 1 here, and 0 is male, kind of more likely to be obese. And then when it comes to family history here, you can see that those here with family history, they tend to be prone to be obese. And then when you see here the third one, which this acronym here measures nothing more than how often they eat food between meals. And I was expecting that these people here will eat a lot of food between meals, but that's not what's happening here. And this will be really good to have some expert that has domain in like human body and physiology to explain why this is not happening here, but I think there was a good example to put it on it. Then I have another scatter plot here for all those 7 classifiers, just so we can kind of see the distribution. I don't want to choose the word distribution, but I think you got my point. And this is a pairwise plot, so we can cross some of the variables here that I got after a lot of iteration. So we can see, for example, that it seems that we have some sort of a positive correlation between weight and height here, and it makes total sense. You can also have an idea about the age here, where the distribution of the age itself, and other variables, some sort of a clustering here already. You can kind of spot them here. We're gonna see that later. And then moving on, I have done another scatter plot here. This is what I think is fun, because I was trying to put weight, age, you know, if whether or not they eat food between meals, and the gender here, so we can kind of see some sort of a pattern among the weight here, and then how women, you know, ladies and gentlemen is kind of distributed here, and some outliers also here, a lot of age and the actual average that we just saw previously. And this plot here shows nothing more than this is actually nothing more than a fancy box plot. If we had any guys here outside this big circle, that will mean we'll have outliers. So for the weight and height, we don't actually have outlier. I have this guy here in the limit, so I could take this guy off of my analysis, but I just didn't, because technically it's still in a good shape here, right in the middle. And then we have some more exploratory analysis. I try to work with some clustering analysis here. So essentially what I was trying to figure out how many clusters we need to do. And when I did this elbow analysis here, as people call elbow method, it was showing 9 clusters. I thought it was too many. So I used the MD, the model-based clustering algorithm, which automatically gives me the number of clustering, and it actually gave me exactly the same number, 9. So that was fun. And that's kind of how they are, excuse me, this is the density of those clusters. But again, I thought there was too many, so what I did next was I got just height and weight, and I put it there and trying to figure out how many clusters I need to work with for that 2 particular variables, and then we came up with 4, and those are the clusters that we have. But by the way, these darker and bigger dots here, they are more uncertain, so they mean like they should be in, you know, cluster, this cluster, that cluster. So that's because we have this, you know, funny colors here, and that's another one that we also saw previously. And then the correlation matrix for collinearity check. I'm not gonna have time to go through in detail, but essentially what I'm trying to see, if you have a highly correlated variables, I want to get rid of one of them, and for that decision we use the VIF scores here. And as a general rule of thumb, if you have a variable with a score equal 5 or higher than 5, then we disregard that variable. But here we didn't have any, so I didn't actually had a chance to remove any of these variables. And moving for the PCA analysis, there's that PCA analysis for all the dimensions that we had here, and that's the biplot for that. So usually what we are looking for is the dimension 1 and dimension 2. What I learned is if they sum up 70% or higher, then this is a good indication that you can actually reduce the dimensionality of the data set by focusing on just those 2 dimensions. And unfortunately, in this case here, we didn't have that. I had to about 27.5% when you sum up these 2, and that's not enough for me to get rid of any other variables so far. And then if you want to decide whether or not to get rid of a variable, that's a good way to do it. You can plot this, which shows the contribution by each dimension here. So you can see weight here, the first one, and the dimension 2 with this variable here called FAF. So that means that, let's say if you had 70% or more, I could, you know, just delete those variables from my data set and clean my data set to what really matters, and that's the threshold here. I also did a logistic regression here because I was not able to, you know, get rid of any variable so far. I thought the logistic regression could give me some intuition about it, and this is the best one that I came up one first after a lot of iterations. So we can see the height and weight here, and all such other variables they are statistically significant here in p-value. So I I got that. I got rid of those two here, and I run the regression again. I got rid of this one here. I run again, and I got these as a kind of final model. I also plot his the regression here, the curve here. We can see it's funny because you see the 90 kilograms. By the way, this is kilogram, not pounds. That's kind of where everybody not obese was sitting. It's kind of funny how we can kind of see this curve here. And then because height and weight was really used to create the regressor here, the predictor, I got rid of height and weight, and what I find out was that many variables, when I did that, many variables was actually statistically significant to predict obesity, and that might be the reason I was not able to get rid of any on my PCA analysis, because they're all kind of, overall they're all important. And again, because I create two classifiers, one with 2 levels and one with 3 levels, I try to use the AIC score to see which one of these models would be the best one. So as you can see here, consider the same number of degrees of freedom, the number with 2 levels, which are these ones that you guys are seeing here, are better than the one with 3 levels. So that was one other benchmark here to see if I'm kind of doing the right thing. And moving on, this is the rock curve for the balanced classifier with 2 levels. So I like Rose package better than Smooth, because Rose allows me to benchmark which option to balancing my classifier I have, which one of them are the best one. So I really love this. I would recommend you guys take a look at that later. And then for the machine learning part, I put it all together, and I came up with this benchmark of different algorithms for machine learning, for trying to see the prediction of my classifier here. And you can see here they were close to 100% or 1 here. That got me very worried about overfitting, because they're like too good to be true. But moving on, they have the accuracy and kappa. I would recommend you guys to look at that for that later. I'm not gonna have to explain that right now. I'm running out of time. But I picked my support vector machine to move it on, although it's not actually the most accurate here according to this. So support vector machine, I also did another benchmarking where I was looking at different types of approach for support vector machines, and the linear one was the one with the best accuracy. This is also shows the cost function here. You guys can look at that later. You can just stop the video if you want, if you will, and kind of see how they look like. I think they're kind of intuitive, I guess. So for the support vector machine, the linear model, which was the best one that we saw previously, you just saw that. So I got one classification here for 7 levels. So in the original data set here, they did a pretty good job in my opinion. And I got one for the 2, it was also good. But for the 3 levels, for some reason, something kind of went funny here, and I'm not trust on this one. But again, that concept of being, quick and fast, fail fast, quick and dirty, and fail fast applies here, because at this point I'm not with the illusion of perfection on top of my head. I'm just trying to figure out get some intuition of the data, and then later on we can definitely explore more the data set and see if we can improve things, and have work on future research and all of that. But for now, I think this is great. Right, so wrapping it up, this presentation, this is here, you can see some summary of my findings. You can read that later, but that was my concern here about overfitting. I hadn't had the chance to test for overfitting to really see if the model is overfitted or not. I didn't have that, because usually, a small data set is kind of tricky to work with, especially when they are balanced using a metric that I would not use mood for that. But in any case, when I figured that I was too late already, and this was my second proposal, so I didn't want to come up with a third one. And the limitations here, again, small data set, and the limitation of a body, and all of that, the balancing with rows and data privacy also. In future research, increased number of observation would be good, and further, investigate overfitting again, and mastering support vector machine would be something for personally, my personal development here. So I'd like to thank you guys for the presentation. See you later.